Hi everyone. So today we're gonna talk about some hidden features in C#.net. We're gonna look at some actually hidden features that aren't really documented, and then we're gonna look at some features that are documented but they're not really known. So you can find them that documentation is minimal or obscure, for example. So what we're going to be looking at is hidden keywords. We're going to have some fun with initializers. We're going to implement default interfaces, which is crazy, absolutely crazy, but we can do it if we wanted to. And finally, we're going to look at a feature called a tuple deconstruction. So let's jump in, I guess, and let's see what we have here. So we have a bunch of, as you can probably see, I have a bunch of hidden, absolutely hidden features here. So there's free keywords that normally you don't see in a program. So they're not gonna be documented almost at all. So what we're gonna do is we're gonna type in make ref, and now it's gonna highlight the keyword, but there's not going to be any intelligence for it and not really any documentation for it as well. So .NET actually has a bunch of these like hidden keywords, and here are the three of the interesting ones, I guess. So it's make ref, ref type, ref value, and there's another one called arglist. And while their utility now is not that great because there's new mechanisms that actually exist in the new .NET Core that lets us do the same thing and solve the problem using the newer methods which are faster. But these keywords were actually really hot in like .NET 1.1, .NET 2.0 times, where what we had actually is say that we had a problem that we, for example, wanted to create a custom memory allocator. Normally, this is not really possible because there's constraints. What we can do is actually like an array pool or memory pool. That's the greatest things that we can do without resorting to these keywords. And these keywords actually, like makeref, for example, will create something that's called a typed reference. And a typed reference is a struct that has, first of all of these interesting things, but it's a struct that actually contains a hidden field here, which we can access. There's no problem. And that's actually a pointer to a object. So that pointer might be to a struct or to a class, for example, on a heap. And people were actually using these keywords to be able to poke like what's in the memory of the heap. They could, for example, see what sort of fields does the object have, and like do crazy stuff like function pointers you can do with this. You can do like swapping objects, casting objects. You can, like I said, do custom memory allocations with different policies and whatnot. So these like keywords are really useful for this sort of like low level stuff. Nowadays, there's better ways. There's unsafe, which is a class that actually lets us do the same things, but more efficiently. So these keywords are not really all that useful anymore. But let's see here. So we have an int32, which is it has a value of 10. When we make ref, so we're gonna have this reference objects. Referenced type. Now we can get actually a pointer to it and start having like fun. But we have the ref type as well, which will actually return the type of the object, which is an int. And then we can have called a ref value, which will return the value, which is 10. So let's actually have a look at a simpler example because we're not going to do custom memory allocation now. So one of the interesting things that you can do with these mechanisms is to actually have something that's called a forced cast. So normally in C#.NET, in order to be able to cast something, it needs to be it needs to be an inheritance hierarchy. But with a forced cast, you can actually cast anything to anything. And you might wonder why this is useful. Where, for example, what we can do here is duck typing. That's the first bit. And then the second bit that people are actually doing is smuggling objects to the places that they have no really access to. And that, depending on how you look at it, that might be dangerous, but people are actually using it for really interesting things, like polymorphic parsers, for example, and stuff like that. So it's useful. So let's look at this cast class here. So we have a class called cast, and we have a method called force cast. Where we're going to be casting class A to class B. So let's look at A and B. So these are just two classes. They're like not inheriting from each other, so they have nothing really in common. But they have a single field. In this case, it's called A and it's 10, and in B's case, the field is called B and it's 20. So what we're planning to do now is we're planning to cast A to B. So how to actually use this mechanism here, right? So let's go to this method. And what we're gonna see here is that our input object, so it's the like new A that we created, we're gonna create a typed reference from it, and then we're gonna create a typed reference of the destination object. So we're gonna just create the destination object, which is gonna be like no, if it's a class, and we're gonna make the reference of the destination objects, and we're just gonna switch pointers around. And now we've actually casted an object. And in order to actually create the value again, we have to use the ref value and just return. And that's gonna be enough to be able to fool the runtime that A is B and B is A. So let's see how it works. So I have a new class called A, and it has a field which just has like A, and that value of A is 10. So now I casted it to B, and as you can see, we still see value 10. We can still see that it actually saying that this is an A, but we have now access to a field called B, which A doesn't really have, and we can assign the value of 100, and we still see A that actually is presenting itself as B, and we have a value in B which is 100. So this is super interesting, right? And what happens when we try to get type of B? So let's actually see when we do console write line get type. So what we should see is actually we should see A. Yeah. Although we're B, but we're actually presented in the type system as A. So now, if we wanted to actually pass something that actually accepts B, for example, not A, then we could take B, and we want to see B here and do something with B. So remember, we had A, now we're actually having B here. So let's go and take B and do this, and let's print B get type. Let's run this code and let's see how it performs. So as you can see, we actually smuggled an object to a method that actually takes B, but instead we passed A, and that's good. So this is the thing that you can do. This is one of the things that you can do actually. Okay, so let's see something else. So there's yet another keyword which is called arglist, and the arglist might give you Perl vibes if you ever code in Perl. So this is the arglist, and it's a method that actually accepts any number of arguments of any type. So this is our argument list here, and in order to be able to access that, we actually need a special struct, if I believe. Yep. That will create an iterator over that argument list, and we can get the next argument, and what we're going to have is a type reference. We can get a type and a value from this, and we can create values as well. from these type references. So what we can actually do is really interesting because we can just pass any number of objects of any type really, and it's going to work. So how do we create the arglist? So what was the method name? So it's arglist. So now let's say that we want to pass something here. So what we have to do is do arglist one bbb, right? And as you can see, it works. So we can pass any number of like interesting arguments here. Let's see if it works. If it doesn't crash, it didn't crash. So as you can probably tell, this is all good. We have the arguments here. There's a number of arguments, but we cannot actually look it up because it's a pointer. But we can get the next arg, so that this is a type reference that will have a reference to our like int value, and if we go get next, then we're gonna get a reference to our string value and so on. So it's really an interesting feature. Like I said, if you programmed in Perl, this is something that you might remember from Perl in a way. And yeah. Okay, so this was a section of like absolutely hidden keywords that you probably shouldn't use if you don't know what you're doing. Let's move to not really hidden and undocumented things. Let's move to things that are documented but not really well known. So one of the interesting bits that aren't well known is the fact that you can do enumerable. You can any class or any struct can be enumerable even without the enumerable interface. So normally what you will do is you will implement this interface, and then you can use a for each loop, for example, in a class. But what's actually interesting is that you don't need that. You just need a method that's called getEnumerator, and that's it. The type of the return doesn't really matter all that much because, as you can see, normally the documentation will say that you need to have a enumerable and you need to return something that implements IEnumerator. But our fake enumerator does not implement any interfaces. It just implements method signatures that actually cover that enumerator interface. So hopefully you see that we don't actually need any interfaces implemented. We just need method signatures in order to be able to turn an object into an enumerable class. So let's just run it. And as you can see, no interfaces, no nothing, just method signatures, and we're going to print out hellos. As you can see, we're printing out a bunch of hellos like infinitely, because our enumerator class, which is fake, will just return hello all the time. So this is useful because you can get around certain problems where you, for example, want to turn something into a enumerable class and it does not support it and the class is not yours. You can actually do that, for example, by using an extension method or just an extension, for example. Or you can actually provide, create a class yourself and provide this functionality if for some reason you don't want that interface, which is interesting. So yeah, let's move to another feature that's not really well described, and this one is an interesting one, and it's like array initializers. So each class can have its own like default initializer, for example. So I have a class called array initializer, and I'm just providing some values to it. And as it turns out, you can do that if you have this time you have to have an interface which is enumerable, and you need to have a method called add. So if we don't have this method, this will not really work. It's not gonna compile. As you can see, it's not compiling. I'm not getting an error because Visual Studio just said nope for some reason, so it does not return errors this time around. Uh, okay, I can live with that, but hopefully I showed you that you need to have a method called add, because if you don't, it's not going to compile. It's not going to let you do that. But if you have that, then let's actually have a breakpoint at this statement, sorry, this function here, and let's see that it actually tries to put stuff. Sorry, I need to comment this out first. So the array initializer calls the method add. 1, 2, 3. Yeah. So as you can see, you could create really interesting stuff here because you can pass objects. Nothing is actually stopping us to pass like very complex stuff here because there's no type system that actually will say that we need to convey to some type. You can have anything here. So you can have like objects, very complex types, interface types. It's all going to work. And you can all create them, which is super useful in a lot of cases because you can actually have these fluent objects in a way that you can create. And with that, there's another interesting initializer which is even more powerful, in my opinion, which is called a indexer initializer. So the indexer initializer means that if we have something that has an indexer, for example, then we can use that indexer to initialize stuff at a given index. So in order to use the index initializer, we just have to have the indexer, and we have to implement like the get and set methods, and it's going to work. So I have a method on set implemented here, so it's going to print the keys and values that we provide to that indexer. So we have just A and B and 1 and 2. So let's actually look at the output of the program. As you can see, we have A equals 1, B equals 2, which is exactly the thing that we have here. And again, you can combine these two, which is super interesting. You can combine the add-in array initializer with the index initializer, and this combination could like provide really interesting class constructors, class initializers. They could be very buggy and very messy and very horrible, but there's a couple of use cases that probably you can find that are worthwhile, and that application actually makes sense. Okay, so moving on to one of the most interesting things, I guess, in this lecture, which is a default interface implementation. So as you can see here, I have an interface. It's a real interface, and I have created an instance of that interface. So how's that possible even? That shouldn't be possible. Why is that possible? Yeah, so as it turns out, not sure if you heard, but the new C# is adding default methods implementation in the interface. But you could actually do that way before in like .NET 2.0 times as well. It's just a very undocumented and low-level feature that shouldn't be used for the things that we use it here. It's used to do com interop, and that's where it makes sense because in com interop, there's interfaces that have like default implementations, so you don't have to provide an implementation. And there's a feature in .NET that actually allows us to do this, and actually basically what it does is treats the interface as an instance because that interface has a default implementation. So let's go to, to that interface. And as you can see, there's a class that actually implements that interface. It's called test, and the interface is itest. And that single method do is doing console write line hello world. But that interface has a com import with its own GUI that every like com import needs, and that GUI needs to be unique to that com import. And it has something that we call a co-class, which is the thing that actually is the default implementation of that interface. And if we provide this interface here, it's gonna treat our interface as an instance because it knows that it needs to use this implementation of this class. And let's verify that it actually works. So hello world, indeed it does work. That's all good. So the question might be, why even use this? Well, the answer is don't. Actually, don't use this. It's like 99% of the time it's pointless unless you're doing com interrupt. If you're not doing com interrupt, well, maybe there's a reason to use this. It would be a very niche reason. So just don't. Just don't. It's like if you want to troll people, that's a good implementation if you're not planning to do like com interrupt. Other than that, yeah, I guess I'm not. Yeah, I don't even see a reason. There's better ways now. Okay, so lastly, let's look at tuple deconstruction. So the new C# allows us to create like these very flexible tuples, and one of the interesting features of those flexible value tuples is that we can actually deconstruct them. So if we have a class, then we can say that this tuple will represent this instance of this class, and it actually can represent multiple states of this class and multiple fields. And the way to do that is called a like object deconstruction. So our transaction objects has a bunch of fields like ID, name, like an array of partial payments, date and time, and a note. So as you can see, we didn't actually provide all of the fields, and we actually provide a field that doesn't exist in this class here. And the reason for this is you can actually dynamically calculate stuff and return it to the tuple. All that you need to do is to create a signature of a method called an implementation called deconstruct. And we're going to provide what fields can the tuple have. And for example, here the total amount is something that's going to be calculated. And we're going to assign some fields and we're going to calculate the rest and we're going to return them. So every time you provide this interface called deconstruct with these out signatures, it's going to what it's going to do is provide a functionality by which we can create tuples to represent these classes. So it has its use cases. I've used it a couple of times to be able to simplify a complex object. Sometimes it's useful to calculate stuff here as well. You can actually pre-cache stuff in this method, so you can cache certain data points. I'm not a fan of that, but I see some potential use cases, but you have to be very careful with that. So that's all for this part. Maybe we're gonna do part 2, where I'm gonna explain in great detail how to use these features and what are the new functionalities that actually replace these make ref, ref type, ref values, and how to use them as well, how to use the unsafe class, and what sort of insanely crazy things you can do with it. And yeah, maybe we're gonna do a custom memory allocation class, for example. So, but for this part, that's all. So leave a like, leave a thumbs up if the video is worthwhile, and yeah, see you in the next video. So yeah, bye.